Today I want to talk a little bit about the colligative property of vapor pressure lowering. We usually focus on freezing point depression, so the freezing point going down, or boiling point elevation, meaning that the boiling point increases when we increase the concentration of a solution. So we're comparing this to the pure substance or the solvent in a solution. As a consequence of this, of the increase in boiling point, then the vapor pressure goes down. So there's this kind of interconnectedness along that equilibrium line on our phase diagram between boiling and vapor pressure. And so if we think about kind of our phase diagram with temperature along the x and pressure along the y, then as I move, kind of as I'm reorganizing my phases there, then my pressure is going to actually go down for my vapor. So I want to talk a little bit about that phenomenon and something called Rault's law, which is related to that and to the concentration. So whereas freezing point depression and boiling point elevation both deal with molality in terms of concentration, so the molal concentration, which is the number of moles of solute per kilogram of solvent, Rault's law uses mole fractions. So when we're thinking about the number of moles of the solute compared to the total number of moles in the solution, then that actually gets us, that ratio is important for Rault's law. So we'll get into that. Okay, so vapor pressure lowering, we usually will talk about it in terms of a change. So by how much is the vapor pressure going down? That's our delta P here, is this vapor pressure lowering term. And the difference then is between, here's the degree symbol, which indicates the pure substance. So this would be the vapor pressure of the pure. So what we'd find on the phase diagram, pure substance for that particular solvent, and then we'd subtract from that the vapor pressure of our solution, and that would give us this change by how much is it going down. Now there's a couple keys to this. So again, we call this vapor pressure lowering, not vapor pressure depression, even though that would mean the same thing. We have to have a volatile solvent with a non-volatile solute. So volatile means that it readily goes into the gas phase. It's pretty happy to go into the gas phase, which means that it doesn't have very strong intermolecular forces. So there's not a lot that's keeping it in the liquid phase. So that's our solvent. And then something that is not as easily kind of vaporizable as a solute. So that's kind of what works best for these sorts of scenarios. We're mostly talking about non-electrolytes. We'll get into some examples in future videos where we take into account things like dissociation and the Van 't Hoff factor. But for our purposes for this video today, we're going to talk about non-electrolytes. So we're talking about things that don't split apart into multiple pieces. We're just talking about kind of pure substances, mostly nonmetals with other nonmetals. Okay, so this is getting us into Raoult's law. There's this relationship then between the partial pressure of a solvent and we've talked about partial pressure of gases in past videos when we've talked about gas law. So this is the partial pressure of the solvent in a solution. And you can tell the difference between the solution versus the pure substance because the pure is the one with the degree symbol. So this is the partial pressure of the pure solvent. So nothing mixed into it. And then this is my mole fraction of however much I have of that. So that's how much of my solvent that I have, my mole fraction. And recall that mole fractions are the part out of the total. So this would be the number of moles of the solvent over the total number of moles. And that would give me a decimal. And that would be a multiplier here. Okay, so this is a relationship that is known based on kind of how the logistics of this work out. So this solution is impacted by this mole fraction, by how much of this I have, and by the partial pressure of that. And the partial pressure of that is important because it's a volatile solvent. So that's an important piece to all of this. So if we're thinking about this and we substitute this in for our delta P here, then I have kind of my pure vapor pressure, my pure substance, and then I can substitute this in here, right? Because this would be this value. So I'm going to put that in here. So we end up with this. Do a little derivation here. Okay. And then if we factor out this value, which is going to be the same for both, then we end up with our delta P is equal to, we'll take this guy out, move 1 minus this guy. And now this is kind of an important relationship, because if I have two components in my solution, then I have kind of the mole fraction of one plus the mole fraction of whatever the other thing is. So let's say that B is my solute. Then if those are the only two things in my solution, then those fractions are going to equal my total, which is 1. So if I was to kind of rearrange this, then my XB here, the mole fraction of my solute, is equal to 1 minus my mole fraction of my solvent. So then if I plug that in to this guy, then I can end up with this, that my delta P is equal to my vapor pressure of my pure solvent times the mole fraction of my solute. Okay, so this is called Rault's law. And it kind of looks like one of our gas laws. So again, how much the vapor pressure is lowering is equal to the vapor pressure of the pure solvent times the mole fraction of the solute. So now we have this relationship that relates the concentration of my solute to how much my vapor pressure is going to go down. Let's look at an example of this. It's the hardest part of my job right here. Oh, there we go. Okay, so if I have a solution that has this tiny amount of naphthalene in chloroform, then what is the vapor pressure lowering going to be for my chloroform? Now I can tell that my chloroform is my solvent because I have more of it. Chloroform is also volatile. We know this if we've watched any kidnapping kind of movies. So chloroform here is volatile. Naphthalene less so. It's still pretty volatile. It's actually pretty stinky. Naphthalene looks like this. It's 2 ring structures. And I'm doing kind of an organic way of drawing this thing where I have a carbon at each of these points and as many hydrogens around them as possible. These ring structures then indicate that there's alternating double bonds. There's delocalized electrons here. This is naphthalene. So the actual chemical formula looks like this. And so my molecular weight is this. My molar mass is that. That's naphthalene. It was a primary component in mothballs for a while, so definitely on the somewhat volatile side because we could smell it, and the mothballs turned out to be pretty carcinogenic, so they've moved away from that in making mothballs these days. Okay, so if I want to use Rault's law, then my vapor pressure lowering is going to be equal to the partial pressure of my solvent times the mole fraction of my solute. So I need to figure out what I'm missing, because what I'm looking for is this guy. That's what it's asking about, the vapor pressure lowering. So what I need is my vapor pressure of my pure solvent. So my solvent, my chloroform here, if I look this up, it has a partial pressure of 156 millimeters of mercury. So that's important information. And now the only thing that I'm missing is my mole fraction of my solute. So I need to figure out how many moles of naphthalene I have over the total number of moles. So the first step to this is to convert both to moles. So this is my napth. 1 mole. And that gives me a tiny amount, 4.02 times 10 to the negative third moles. And then I have my 60.8 grams of chloroform. Now the chemical formula for chloroform is CHCl3, so that's trichloromethane. And the molar mass for that is 119.37 grams per mole. And that gives me this, 5.9 moles. All right, so my mole fraction then is going to be equal to, for B, which in this case is my naphthalene, this is my B, then I need to take my number of moles of naphthalene over the total number of moles. And that'll give me some sort of ratio here. So my total number of moles doesn't change all that much. It just ends up being 0.513. And so my ratio ends up being 0.00784. That's my mole fraction of my solute. So that's my XB. I have my vapor pressure for my pure solvent. So multiply those together. That's Raoult's law. And we end up with 1.22, and I'm in millimeters of mercury. And again, that's just because that was the pressure unit that I was given for this, which is totally fine. We could convert that to something else if we needed it in atmospheres or kilopascals or whatever else. But that's by how much my vapor pressure is going to go down. So it's going to decrease by this amount. And that's the way we use that. So kind of handy, kind of straightforward. And if we're thinking about this in other contexts, then we want to know like when this would work. When do we follow these kinds of rules? And how does this relate to other gases? Well, we have what are called ideal solutions, and it's similar to what we're talking about with ideal gases. So an ideal solution follows Raoult's law for all mole fractions of A and B, and this usually occurs when the solute and the solvent have similar intermolecular forces. So the more closely related the solute and the solvent are, then the more closely aligned this solution will be, the more ideal this solution will be. If you have two things that are really different, they aren't really going to mix all that well, right? That's that kind of golden rule of solubility, like dissolves like. But an ideal solution, these things fit really well together, and we can use Raoult's law to talk about the vapor pressure. So we can show the total pressure of the system using Dalton's law. Dalton's law of partial pressure says that the total pressure of the system is equal to the sum of the partial pressures. And we know from kind of the Raoult's law relationships that that would be equal to this. Here's the vapor pressure of the solvent times the mole fraction of the solvent plus the vapor pressure of the solute times the mole fraction of the solute. So we can use this relationship too to solve problems that look like this. So now if I have a mixture of benzene and toluene, which are both kind of really nasty organic solvents, then we have these mole fractions for each. So we have benzene and toluene. Benzene, there's a greater amount of it, so that'll be kind of my A is 0.7, and then my B is 0.3, and then my partial pressure for benzene is 75, and my pressure for my toluene is 22. Again, we're in millimeters of mercury here just because that's what we're given. And then if we plug and chug in our new fancy schmancy Dalton's law, Raoult's law hybrid here, then we end up with a total pressure of 59 millimeters of mercury. Okay, so that's one way that we can use Raoult's law when we have a mixture like this and it is an ideal solution. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.